Good morning, respected sir, and my dear friends. Today I am going to present my case study on railway signal interlocking using logic gates. This project is based on applying digital electronic concepts to improve railway safety systems. Through this presentation, I will explain how simple logic gates can be used to prevent train collisions and accidents also. So, introduction. Railway transportation is one of the most widely used and economical modes of transport in the world. Millions of passengers depend on it daily for travel. Because of such heavy usage, safety becomes extremely important. Even a small mistake in signaling or track control can lead to serious accidents. In real life, many railway accidents happen due to miscommunication or human error. To avoiding such situations, automated systems like signal interlocking are used. Interlocking. What is interlocking? Interlocking is a safety mechanism used in railway systems. It ensures that signals and track switches operate in proper conditions or proper coordinations. Basically, it acts like a safety lock between different tracks. It makes sure that two trains are not allowed to use the same track at the same time. This helps in preventing collisions and ensures smooth railway operations. What is the need for interlocking? Interlocking is required to prevent train collisions at junctions and also at some platforms. It helps and avoid incorrect switching of tracks. It ensures the safety of passengers as well as railway staff. It also reduces dependency on manual control, which can lead to errors. Therefore, it is a very important part of modern railway systems, which is interlocking. So now let's discuss on types of interlocking. There are three main types of interlocking systems. The first is a mechanical interlocking, which is manually operated and used in older systems, as you can see in the image also. Second is relay-based interlocking, which uses electrical relays, which can also be seen by in the image. Third is an electronic interlocking system, which uses digital circuits and is used in modern railways. Electronic interlocking is more reliable and faster compared to the other types. Why use the logic gates? Or we can say the role of logic gates in interlocking. Logic gates are the basic building blocks of digital systems. They operate using binary values which are 0 and 1. In railway signaling, we can represent signal states using these values, such as red and green. Logic gates help in making fast and accurate decisions. They are used to automate the interlocking process and improve system reliability. So let's talk about basic logic gates. The basic logic gates include AND, OR, and NOT gates. The AND gate gives the output only when all inputs are high. The OR gate gives output when at least one input is high. The NOT gate gives the inverse of the input. These gates from the foundation of digital circuit design. Now let's discuss on additional logic gates. Other important gates are NAND, NOR, and XOR. NAND and NOR are called universal gates because they can be used to implement any logic function. These gates are widely used in designing complex digital systems. NAND gate when output is 0 only when all inputs are 1. XOR output is 1 only when all inputs are 0. XOR output is 1 when inputs are different. These gates enable complex interlocking logic designs. Now Now let's talk about problem statement. Consider a situation where two trains are approaching a railway junction from a different direction at the same time. Since only one train can pass safely through the junction, there must be a proper control system so to avoid the accidents. If both trains are allowed to move simultaneously, it can lead to serious collisions. In busy railway networks, such situations occur frequently. Without automation, it becomes very difficult for humans to manage this safely. Therefore, a reliable automated system is required to control signals and prevent conflicting train movements. Here here are the inputs and outputs. In this system, we consider two inputs. A represents the occurrence of track A and B represents the occurrence of track B. If track A is occupied, the input becomes 1, otherwise it is 0. The outputs are SA and SB, which represents the signal of each track. These outputs decide whether a train should stop or move. Now we talk about safety conditions. If track A is occupied, signal A must be red. If track B is occupied, signal B must be red. Both trains should not be allowed to move at the same time. Only one safe path should be active at any moment. These conditions ensure safe railway operations. So here is the truth table, which is the most important part. This truth table shows all possible combinations of inputs and outputs. Let us understand it step by step. When A is 0 and B is 0, both tracks are free, so both signals are green. When A is 1 and B is 0, track A is occupied, so its signal becomes red while track B remains green. Similarly, when A is 0 and B is 1, track B is occupied, so its signal becomes red. When both A and B are 1, both tracks are occupied, so both signals are red. This ensures that trains do not collide and safety is maintained. Uh, Now we'll talk on Boolean expressions. From the truth table, we derive the Boolean expression SA equals not A and SB equals not B. This means that if a track is occupied, its signal automatically becomes red. This shows how simple logic can control a real-world system. These expressions demonstrate how track occupancy directly controls signal states. When a sensor detects a train, the input is 1. The NOT gate inverts this to output 0, preventing the other trains from the collision or entering the wrong uh, track path. Now we will study about the logic circuit diagram using NOT gate implementation. Circuit diagram using NOT gates for input A and B. Track occupancy sensor A and B connect to NOT gates, producing inverted outputs. So now we will study about the working of this system. The system continuously monitors the track conditions. As soon as a train is detected on a track, the signal turns red. If the track is free, the signal remains green. This process happens in real time without delay. It ensures that only one train moves at a time, preventing other trains from entering and also prevents the collision between the trains. Now we will talk about real life implementations. In real life systems, the concept is implemented using electronic interlocking systems. Sensors are used to detect train positions. These systems are connected to control rooms and signaling units. They automatically control signals and ensure safe movement of trains. So here are some of the advantages of logic gate interlocking. Benefits of digital signal control. The first one ensures high safety by preventing conflicting train movements, provides fast and real-time response, eliminates human errors through automation, simple and efficient circuit design, offers a reliable and consistent performance, easy to maintain and troubleshoot, can be expanded for larger railway systems. Now we will discuss some of the limitations which is faced by interlocking systems. The challenges are complex systems. Large railway networks require interactive circuit design with multiple gates and connections, which can cause some of the challenges. Second, maintenance required. Regular inspection and testing needed to ensure reliable operations. Third, sensor dependencies. System accuracy relies heavily on proper functioning and track occupancy sensors. Environmental factors. Harsh conditions can affect sensor and circuit performance also. The system can become complex for large railway networks too. So now let's talk about the future scope. In the future, the system can be enhanced using artificial intelligence and IoT based systems. AI can help in predicting train movements and avoiding congestions. IoT can enable real time monitoring and remote control. This will make railway systems smarter and more efficient. To conclude, railway signal interlocking using logic gates is a simple yet powerful system. It helps prevent accidents and ensure safety train movement. The project shows how digital interlocking can be applied to real world problems. Safety in railways through smart digital logic.